This is the last lesson in Unit 6 to do with z-scores and normal distribution. In this lesson, we're going to look at how we can actually use z-scores and the normal distribution to help us answer problems to do with discrete random variables. The lessons we've been looking at up till now have all had to do with continuous random variables, things that can be measured like time or volume. In the past, previous units, we've looked at discrete random variables. We've looked at things like binomial distributions and hypergeometric distributions, where we could get probabilities from various formulas for discrete random variables. So the idea for today is that we're going to be able to use z-scores and apply them to discrete variables. We're going to have to make a few adjustments in order to do it. And the benefit of being able to do this is if we needed to calculate a probability that has to do or that would require a lot of calculations, say I wanted to find the probability that out of, I don't know, say I had to calculate a probability that involved getting 6 or 7 or 8 or 9 or 10 or 11 or so on. So in other words, a whole bunch of different outcomes. Rather than having to calculate each one separately and add them together, I can lump them together using a normal distribution in z-scores. And it'll be an approximation, but it'll be very close. All right, so that's the idea. So to approximate the binomial distribution, remember binomial distribution is when you have independent discrete variable with a normal distribution. We still need to calculate z-scores, and if you remember, z-scores are calculated, if I'm using the population, it's x minus mu over sigma, which is mu is the mean and sigma is the standard deviation. So I need to get an average and a standard deviation. So these two formulas here, we can calculate the mean of a discrete variable distribution using mu is equal to n times p. In other words, the population size times the probability of event occurring. We can get the standard deviation by doing, pardon me, the square root of n times p times q. And those are both acceptable approximations. All right, so they're very simple to do, and then we've got those so that we can then plug them into a z-score and then calculate a z-score from them. So that'll make things easy. We can also, we can't always use a normal distribution approximation for discrete random variables. Sometimes the sample size is too small, or maybe it's not normal enough. In other words, it's skewed one way or another. So the way that we can tell if it's close enough to normal and big enough sample size is by doing these two little tests here. If we do n times p, and that's again population size times probability of event occurring, if that's greater than 5, then that's one thing we have to check off. If n times q, population times probability of failure, is also greater than 5, that's the other box we have to check off. So these two things I've highlighted in green are things that we check before we can do it. So they're rules or checks that we have to make sure that we've balanced. Then there is hypergeometric distribution. Hypergeometric distribution was also for discrete random variables. However, that was for dependent events. If you remember, things like if you're dealing out a hand from a deck of cards where you're not putting the cards back in, then what happens is every time you deal out one card, then you change the probability for the next card. And there's formula for doing that directly, but again, we might want to do an approximation of it to make things a little more simple. And again, we still need to go back to this z-score formula, so I need the mean and standard deviation. Mean is again n times p, so that's easy. And standard deviation, though, sigma is a little bit more. It's certainly not, it looks awkward, but it's certainly not that hard to calculate. n times p times q, which is exactly the same as this one up above, but we also have to multiply it times by np minus n divided by np minus 1. And n is the sample size, and np is the population size, as you can see here and here. And again, we have to make sure that it's reasonable to do it. And so for a hypergeometric distribution, we can tell if it's reasonable to use this approximation as long as the sample size is less than 1/10 of the population. That's what this formula says, since NP is the population. Since binomial and hypergeometric distributions are discrete, but the normal distribution is continuous, we have to apply what's called a continuity correction. For example, if you want the probability of rolling a 6 exactly 3 times, if it was a continuous, we can't imagine we're rolling a die. Let me back up for a second. We're rolling a die, and obviously this doesn't say how many times I'm rolling it, but let's imagine that I'm rolling it 10 times, and I want to find the probability of rolling it, this 6 exactly 3 times. I can do that. I could do the binomial distribution for that because it's because it's independent. We know for a continuous probability that or continuous distribution, the probability of rolling or getting anything one number exactly is 0. We've seen that before, but again, now we're not dealing with continuous distribution. We're dealing with a discrete one. So of course there's a probability associated with rolling a 6 exactly 3 times. So the way that we calculate it, since any single thing on the normal distribution is 0, any single probability is 0, we give ourselves a range. So if we want to find exactly 3 times, what we do is we actually find the probability between 2.5 and 3.5. So in other words, halfway between 1 unit below and halfway to 1 unit above, giving us, if you can imagine the graph, in fact, you don't have to imagine it, let's draw it right now. So imagine that rolling a 6 exactly 3 times came here on a normal distribution. Remember, I'm imagining that I've rolled a die 10 times overall, so 3 times, I don't know, actually where this would fall, but let's pretend that it was here. There's no width to this line, right? So I can make myself have a bar by going down to 2.5 and up to 3.5 and finding the area between those two, and now I can get the probability. And you'll notice that this bar has got a unit width of exactly 1, from 2.5 to 3.5. So that's how we get around that. And that's called the continuity correction. If we want the probability of rolling at least 3 6s, well, now we want something that's more like this. Again, let's say 3 is here. If I want at least 3 6s and I wanted to include 3 and up, well, then I would just go down to 2.5. I'd drop that half unit again, but this time I'm going to go all the way up to here, and I want this whole area here. However, if I want the probability of rolling more than 3 6s, without that at least idea in there, so we're no longer including the 3, it would look like this. Again, here's 3, but this time I go to 3.5 here, and again, I want more, so it's still color in this area, but it's the difference between including the area between 2.5 and 3.5 or not. So this is how a continuity correction works. We only use continuity corrections when we're approximating a normal distribution for a discrete variable. So we only ever use a continuity correction for a discrete variable. That's something that some people have trouble wrapping their heads around. So try to keep that in mind. All right. Let me just get rid of this because it's going to be in the way of some other sketches I want to draw. Stacy rolled a die 36 times. she records the number of times that the die shows a 4. Is it reasonable for to approximate this distribution using a normal distribution y? Okay, well, before we even get to that, if she's rolling a die, we know that it's discrete, right? Rolling a die is definitely a discrete variable, and they're independent trials. Every time I roll a die is completely not influenced by any previous die rolls I've had. They're all independent, so that makes it binomial. Is it reasonable to approximate this distribution with the normal distribution? That's where we go back to NP being greater than 5 and NQ being greater than 5. As long as that's true, then we'll be able to say yes. If not, then we'll have to say no. So let's see what NP is. N, by the way, is 36. That's our number of trials. And the probability, P, is going to be, we're looking for 4s, right? So it's a 6-sided die, and we're looking for the probability of getting a 4 on any single roll is 1/6. So there's my P. So NP equals 36 times 1/6, which equals 6. And 6 is greater than 5, so that's good. NQ is going to be 36 times 5/6. Remember, Q is just the difference between P and 1, so 5/6. And so that would equal 30. That's also greater than 5. So the answer here is yes. It is reasonable because NP and NQ are both greater than 5. So that was the first thing. We checked to make sure that we're allowed to use this approximation. Next, if we're going to do the approximation, we need to have a mean and a standard deviation so we can calculate z-scores. So remember that the mean is just also equal to NP. We've already calculated that. So we know that's 6. Sigma, the standard deviation, is equal to NPQ. Well, since we already know that NP equals 6, I can just fill that in and multiply that times 5/6 for Q. And then when I take the square root of it all, I get 2.24 to 2 decimal places. So there's my mean, there's my standard deviation, and we're going to use that for z-scores. Next part, we want to determine the probability that the die will show a 4 at least 5 times. All right, let me draw my sketch over here. Again, I always draw a normal distribution just so I can visualize. If mean is 6, then we know in a normal distribution that would be here in the middle. And we want to find the probability that they're going to roll the 4 at least 5 times. So 5 is here. At least means I'm going to want the area to the right of wherever we're measuring from. But where are we measuring from? That's the question. And the answer is, due to the continuity correction, we're actually going to measure from 4.5. And it's 4.5 because of the fact that we want at least 5 times. In other words, we want to include the 5, so we go a bit below it. And so we want this area here. And from here, now that I've got that, then it's going to be just what we've done before with z-scores and z-score tables. This, by the way, this 4.5 becomes our x value that we're going to use. So z equals 4.5 minus the average, which was 6, divided by standard deviation, 2.24, that works out to be 1.11. Sorry, I had it worked out ahead of time and looked at the wrong number. That works out to be negative 0.67. And then we can, use our z-score table, from our z-score table, we know that the probability that x is less than or equal to negative 0.67 is, let's go find it. Some previous highlighting that I want to get rid of. So let's find negative 0.67. Negative 0.6 is here, and 7 is this column here. So it's 0.214, right? Sorry, 0.2514. 0.2514. That's the probability that x is less than or equal to 4.5. But we don't want less than. We want greater than. What we're actually looking for is the probability that x is greater than 4.5. So that's actually going to equal 1 minus the probability that x is less than or equal to 4.5. Which works out to be 0.7486. And I realize, well, actually, let me just wrap this up. So we have a probability of 0.7486, or approximately 75% probability of getting at least 5 4s when we roll. The one thing I wanted to clear up here is I realized that that's a bit confusing here where I wrote that x is less than negative 0.67. That's not true. It's the z-score associated with it. So I'm just going to fix that to hopefully avoid any further confusion. So we actually want the probability that x is less than or equal to 4.5. But that's associated with this z-score. And it still remains that, therefore, the probability of it being greater than 4.5 is 75%. And that fits our sketch, right? It looks like I've shaded in approximately 75% of my sketch. And it's a rough sketch, but it coincides, it matches up with it. What's the probability that a die will show 4 exactly 8 times? Well, remember, this is discrete, so it is possible. There is a probability associated with that, as long as we incorporate the continuity correction. We've already calculated in part B the average and the standard deviation, so we can reuse those. So here's another sketch. Here's 6, our mean, and we want exactly 8. So let's say that 8 is here, which means with the continuity correction, I need to go from 7.5 to 8.5, find that area there. So I'm going to have to do 2 calculations. Really what I want to find is the probability that x is greater than 7.5, less than 8.5, which is the same as the probability that x is less than 8.5 minus the probability that x is less than 7.5. So I have to do 2 separate calculations, use the z-score table twice, get the 2 probabilities, and subtract them. So let's do the rough work over here a bit. So for the first one, for z-score, for when x is 8.5, That works out to be, there's the 1.1 that I tried to write down before. There's my first z-score, the probability going along with that turns out to be 0.8665. And then my z-score when x is 7.5 is 0.67. So from the table, and again, I've already got this. Obviously, we should be referring back to the table for 0.67 and 1.1 for these z-scores to get the probabilities. But in the interest of making this lesson a little shorter, I've already got that for us. So the probability associated with that was 0.7486. So if we use a little highlighting just to make things jump a little bit out and hopefully be a little bit more clear where they come from, then I want to subtract the one I've highlighted in blue. I want to subtract the one I've highlighted in green from the one I've highlighted in blue. The difference between those two probabilities is the probability that we're looking for. So it's approximately 12%. So there's approximately, using our approximation, it's about 12% probability that we're going to roll 4 exactly 8 times. Now remember, we don't need to use this normal distribution z-score thing in order to do a binomial one. We can just do it directly using our binomial distribution. In fact, it's easier, but that's only because we're finding a single value 8 times, right? So in a case like this where we're finding it exactly 8 times, I wouldn't bother using the approximation using the normal distribution. But again, I'm just showing how it works right now. So let's compare it. So I'm just going to answer this part here where it says compare the results to the calculation using the binomial distribution. So I'll do that over here. So it's been a little bit since we've done the binomial distribution. We want to find the probability that x equals 8. And remember, we use combinations, we use P and Q. So it's going to be 36 trials, choose 8 successes that we want to have. The probability of success on a single trial is 1/6. We raise that to the exponent 8. The probability of failure on a single trial is 5/6. We raise that to n minus 8, so 28. Put that all in the calculator, it works out to 0.109, or approximately 11%. So, as I said, a lot quicker, I'm done. And if I compare this to this, they're close, right? And it's a lot, the one I've done in red, the binomial distribution, is more accurate and it's easier. So again, in this case, I definitely would use just the binomial distribution. But we're illustrating a point. Imagine, again, in this situation, instead of saying, what's the probability we're going to die exactly 8 times? What if we wanted the probability of, say, rolling for, say, 16, 17, 18, 19, 20, 21, etc., all the way up to 36? Even if I did the indirect method, I'd still have to do about 15 or 16 different calculations. That would be a case where using the approximation would actually save us time. But the point is they're close, right? Okay, one more example. Paul has a drawer full of unmatched socks. The drawer contains 30 blue socks, 30 green socks, 30 yellow socks. So, all in all, Paul has 90 socks, doesn't he? So you call that NP. NP equals 90. Paul is a she. She pulls 7 socks from the drawer and records the number of blue socks in the sample. All right, so pulling socks out of a drawer without putting them back in makes it a dependent situation. And again, it's discrete for sure. Is it reasonable to approximate this distribution with a normal distribution? Well, remember what we're looking for is that we want n, which is the sample size, to be less than 1/10 of NP, which is the population. So 1/10 of NP equals 1/10 of 90, which equals 9. And so NP, 1/10 of NP is greater than n in this case. 9 is greater than 7. So that is good. And that's really all we're looking for in this case. So yes, again, it is reasonable. N is less than 1/10 NP. Determine the mean and the standard deviation of the normal approximation. Remember, for a hypergeometric situation, mu is again just NP. And n was 7. P is, what is P? Oh yes, we're looking at the socks. So there's 1/3 of each different color. So 1/3 of the socks are, what was it, blue? Yes, blue socks. So 1/3, there's 1/3 of the components are successes. So 7 times 1/3, which is 2 1/3, 2.3 repeating, that's our mean. Our standard deviation is equal to NPQ times NP, uppercase NP minus N. Well, let me just write it out again. Not a lot of room, but probably for the best. NPQ times NP minus N over NP minus 1, and we take the square root of that. All right. Well, we already know that N times P is 2.3 repeating, so that saves us a little work. Q was 2/3. Those are just the proportion of the rest of the socks. Remember, NP was 90 minus 7 over 90 minus 1, and then we're going to take the square root of all that. And again, following order of operations is just calculator work, type it in. It turns out we get 1.20. So that would be our standard deviation. Again, if you're confused about where P and Q came from, just remember P is just going to be the 30 blue socks divided by the 90 socks altogether. That's where I got 1/3 from. Q was the 60 non-blue socks divided by 90. That's where the 2/3 came from. What's the probability that exactly three socks, will be blue? Compare this result to calculating the probability using a hypergeometric distribution. Let's start by doing the hypergeometric distribution, because that's, again, finding a single value like this is actually going to be fairly easy. And again, I wouldn't really use the approximation in this case. It's just to serve, for comparison. But let's start with this. And I'll do this in red like I did last time, just to make it stand out a bit. So we want the probability that x equals 3, because we want 3 of the socks to be blue. So remember, the probability for hypergeometric distribution, it's total number of successes, and then we choose the number of that we're looking for, so possible successes and how many we want, times number of failures, possible, choose the number that we want of that. And remember, we wanted to get 7 altogether, or 7 trials. And we put that over 90 total population, choose 7 total number of trials. Really, it's a quick calculation. Type that in and you'll be done in a few seconds, 0.265, or approximately 27%. Okay, that's the easy way for this one. Using the normal approximation, in this case, is going to be more work. So first, let's draw a sketch. Same as in the other one. We put our mean here, 2.3 repeating is in the middle, and we want the probability of getting exactly 3, which means that we have to do a continuity correction and go down to 2.5 and up to 3.5. And so it's just like what we did in, I guess it was example 1D, where I'm going to have to calculate the z-score twice. So what I want is the probability that x is between 2.5 and 3.5, which I have to calculate by doing the probability that x is less than 3.5, take away the probability that x is less than 2.5. So my z-score for when x equals 3.5 would be 3.5 minus 2.3 repeating over, what was it, 1.20, 0.98, which from the z-score table works out to be 0.8365. Again, I've looked it up ahead of time, but if you were actually answering this question, then yes, of course, you'd be referring back to the z-score table and finding 0.98 on the z-score table. Well, since I'm here, I might as well just point it out, 0.98. So that would be here and all the way over to here, I guess, so 0.8365, right? Which is what I already wrote here, 0.8365. So anyway, it's meant to save time. And then I have my z-score for x equal to 2.5. That works out to 0.14. Get the probability that goes along with that the exact same way. And it works out to be 0.5557. Again, maybe a little highlighting just to make it hopefully connect a little better. And so I want to take away 0.5557 from 0.8365. And for that, that works out to be 0.2808, or about 28%. Again, if we compare these two things, they're really close. And again, I would not use the approximation normally in this situation, since the actual hypergeometric distribution is much easier. It's when we have to do multiple ones that's going to be time saving. Here's an example that'll save us a little bit of time, possibly. Even still, finding it for 3 or 4 or 5 stocks is sort of 6 to 1, half dozen the other, whether it's going to save us time to do it one way or the other. But again, let's use the normal approximation to the normal distribution for this one. So 3, 4, or 5 stocks means that here's my mean, and so 3 is here, 4 is here, let's say 5 is here. We want 3 or 4 or 5, so the lowest we would go would be 2.5. We have to do a continuity correction a little bit below that, and we need to go up to 5.5. And I don't need to do a continuity correction for each one because they're butting up against each other. I just need to do this entire area between these two. So it's just like the last example I did, except it's got a it's covering a span of 3 units rather than just 1 unit. But otherwise, I'm going to do the exact same thing. So I'm going to go, let's go through it quick if possible. I want the probability that x is between 2.5 and 5.5, which is the same as probability that x is less than 5.5. Minus the probability that x is less than 2.5. So then again, I need the z-scores for those. Two 2.5, did I already calculate that one? I guess I already calculated 2.5 a little bit earlier on, didn't I? That was the one that had a z-score of 0.14. So I already know the probability for that one was 0.5557. So stick with my color code. And the difference between the two of them is 0.4402, or about 44%.